Okay, thank you for the introduction. I'm Yeye from Microsoft. This is a joint work with Jupen. This is about automatically detecting data errors in tables. So data errors are extremely common. Studies report staggering numbers, such as 90% of spreadsheets that are reasonably large have errors. And also, even 24% of spreadsheets from professional firms like KPMG have errors. So the traditional approach to this is that if you have a high-value data set that's important enough, you hire an expert to do this for you using things like data quality rules and ML models, which are developed in this community. Now, these are all great and super helpful, but there are also millions of spreadsheet users who are end users that may not be able to understand or leverage those data quality rules. So we ask this question of whether we can help them to automatically detect errors. In this work, we try to detect a very specific type of error. So given a column C, we want to detect values from that column that are incompatible with the rest of the column. Clearly, this is not meant to capture all types of errors that have been considered in the literature. The key requirements in this problem is that, first of all, we need to predict errors at very high precision because we don't want to bug end users with all kinds of spurious errors. And in addition, this needs to be automatic, and we have no experts in the loop. So how can we pull this off, right? So our intuition is that we have large corpora of mostly clean tables, and maybe we can learn from those tables what clean tables should look like, and use that to predict errors. So we think we have a promising algorithm. So let me fast forward and tell you what we find in the experiments. We run our algorithm on two data sets. The first one is relational tables extracted from Wikipedia, which are supposed to be like encyclopedia and supposed to be high quality. The second one is Excel spreadsheets crawled and extracted from a large enterprise, and these are supposed to be professional quality. Surprisingly, we were able to detect tens of thousands of real errors at a very high precision. And the labeled Wikipedia dataset is actually released on GitHub, and you can find a link to it in our paper. So here are some of the real examples we detected on Wikipedia. You can see a screenshot of the table and a red circle highlighting the erroneous cells. In this case, it's a datetime value that's formatted differently from the rest of the column. And these are all real tables, by the way. You can follow the link at the bottom to see the table on Wikipedia. So here's another example, and you can intuitively see why this may be problematic. And here's a cell with missing parentheses, incompatible dates. And I hope you can see in the back, but here the value has a dot instead of a column. So we also show cases from real enterprise spreadsheets. The few values marked in red have an extra space. These can be actually problematic if you are doing a group by on this column. And in this case, you have phone numbers that are in different formats, so on and so forth. So I hope you get a sense of the type of errors we can detect. Now, in the time that remains, I will try to give you an intuition of how this works. So the key question comes down to predicting whether two values are compatible or not in the context of the same column. In a previous example of these two values, intuitively we know these are dates and they are not compatible, and they probably should not co-occur in the same column. However, this is a very subtle thing because the second pair of value here, it's actually a lot more likely to be compatible because the first can be a floating point number and the second one could be an integer, and they co-occur all the time in the same columns. So only looking at the pair of values and their patterns is probably not going to be enough. And we find that manually defining those complicated rules of saying what values are compatible with what is going to be too difficult, and it's just not going to work. So that motivates us, the data-driven approach, to detect errors using a large corpus of tables. So let me give you a concrete example. For this pair of values, we use a standard generalization hierarchy, and we encode those values into patterns. So for example, if we choose this generalization, which encodes numbers into digits, then we get, for the first value, 4-digit dash 2-digit, and the second one is 4-digit. Now, if we compute the statistical occurrence of these two patterns, we'll see that the first one occurs 10 million times in our corpus. The second one, it occurs 4 million times. But the two of them actually only co-occurred 50 times within the same columns. So now you can apply all kinds of statistical tests, be it pointwise mutual information or chi-square tests. And they will all point out that the co-occurrence is substantially less than what's expected. So you would be able to say that these two values are probably incompatible. Now, if you look at the second pair of values, we could do a similar exercise and find out that the two patterns actually co-occur a lot more often, and that gives us evidence to say they are probably compatible. So in theory, you need to compute all pairs of patterns and materialize all of those into a big table. And this is only one possible generalization hierarchy. There are actually a total of 36 such generalization strategies. For example, instead of keeping all the punctuation, I can generalize them into a wildcard. So in that case, you would have a different table encoding all the different statistics for the second strategy. So that takes a lot of space, and because we need to be interactive and these need to be in memory, so we face a lot of trade-offs in terms of sensitivity, precision, and space. I won't have time to go into the details. But with that in mind, we formally define the problem as given a table corpus T and a set of generalization strategies G induced by the hierarchy H, we want to select a subset of the strategies such that we can detect as many errors as possible, subject to the constraints including memory constraint and precision requirement. So I won't have time to go into the details, but I will just mention that we use ideas from distant supervision to calibrate the precision of each generalization strategy, and we have a constant approximation algorithm for this problem. So for the experiment, we took a 0.5 sample of the Wikipedia tables, and we run a lot of algorithms, including our own approach, and we manually labeled the first 1,000 predictions. And as you can see, so the x-axis is the top k, and the y-axis is the precision values. We actually have results that are very accurate. In conclusion, we propose an automatic method to detect errors. This is intended for end users. And we use distant supervision and a corpus-driven approach that can detect a class of errors. This actually partly reaffirms previous studies on the prevalence of data errors. We are actually surprised to see such a number of errors in those tables. So that's the end of the talk. Thank you.
Any questions?
Hey, Abdu, University of Pennsylvania. Very important and much needed work. Thank you. So I'm just wondering about your assumptions about tables and spreadsheets. I spent about a year and a half in my PhD trying to extract tables out of spreadsheets.
Yeah.
I actually had to use machine learning to do that. So when you say your input set is a set of tables, do you have to do any extraction on tables, or you assume that a spreadsheet is a single table?
Right. So fortunately, we are in a company, and there are like different groups doing all kinds of stuff. So the Wikipedia tables, it's already extracted from a pipeline which uses Bing syntax. And for spreadsheet tables, it's also extracted with a lot of non-trivial extraction algorithms, as you mentioned. So in this work, we are not focusing on that aspect, but certainly that's very important problems as well.
All right, thanks.
Okay, so that's